Hello everyone, welcome back. So, here is our second group problem. Remember, grab an imaginary friend if you don't have anyone nearby to actually work it with. So starting from rest, we have a bicyclist. He's traveling along, she's traveling along a horizontal circular path with a radius of curvature of 10 meters. At a speed of velocity is equal to 0.09 t squared plus 0.1 t. What's the note? Oh, it is a woman. The magnitude of her velocity acceleration when she has traveled 3 meters. So, how are you going to do this? Well, you're going to write down your equations. You're going to plug in everything you know, and you're going to see if you can go from there. Most likely, getting that we have this equation, you're going to have to take a time derivative, which isn't going to be that bad. Go forth, see if you can do it, and then come back and check. So, 3, 2, 1, and you're back. Okay. Now, one thing I didn't mention, because I wanted to see if you would notice it, is that we have an issue. It told us to get all the velocity and acceleration when they've traveled 3 meters. Not after 3 seconds. No, so when they travel 3 meters. Now, we don't know what the path equation is. However, we can integrate the velocity to find the position function. So we do that. That's not too bad. Now, you might be wondering, like, well, where was our constant? Because we just did this, in terms of t. Well, we know that our initial position, S0, is simply going to be equal to 0. We haven't gone anywhere when t equals 0. So that is our initial condition. That's how we're able to get rid of one of our unknowns. Okay, so we took this integral. We know what this is. And now we have to figure out, well, what time have we moved 3 meters? Okay, what time have we moved 3 meters? So, we do this, we try to calculate, and when we solve for t, we'll get 4.147 seconds. Only one of these responses, it is cubed, so there's probably more than one answer. Only one of these responses will make sense. So, pick the one that makes sense. Beyond that, we can then plug that into our velocity equations to figure out what the velocity is at 4.147 seconds. So it comes out to be 1.96 meters per second. Okay, so that's the velocity, but we still have to find the acceleration. So we did an integral, guess what? We have to do a derivative as well. So we write out our equation, we know, okay, well, the tangential component of the acceleration is v dot. We have everything we need right here, so we only need to figure out that v dot. So we take a time derivative. So 0.09 t squared plus 0.1 t ddt is going to be 0.18 t plus 0.1 meters per second squared. We plug in our 4.147 seconds. We got that from solving our position equation. And we get that the acceleration in the tangential direction, this is only one component, do not stop here, is 0.8465 meters per second squared. Okay, we already knew rho. That was from the problem statement. We know what the velocity is at this particular time because we already calculated it. It's just the magnitude of velocity because there is only ever a tangential component of velocity. That was 1.96, and we square it, and then we have our acceleration in the normal direction, which is 0.3852 meters per second squared. If we want to, we can take the magnitude. If you're wondering why don't I do this with velocity, it's because the normal component of the velocity is equal to 0, as is the binomial. There's only one component to velocity, and that is the tangential, which is why we don't have to take the magnitude for these kinds of problems. But we do with the acceleration because it has both a tangential and a normal component. And that is it. That is the solution to this problem. So you're going to see the exact same steps in all of your homework problems and even in the assessments that are using these equations. It's usually just making sure that you do the derivatives right, do the integrals right, and occasionally a chain rule or having to realize that you have a constant acceleration or something to help give you that extra little push. So I hope this helps you, and I'll see you all next time. Have an absolutely wonderful day. Bye-bye.